Okay, so let me introduce Franz Paschke. Is that right pronunciation? Paschke? From the Technical University of Darmstadt. So Franz studied civil engineering at the TU of Darmstadt, and he is now a researcher at the Institute of Structural Mechanics and Design in the Glass Competence Center in Darmstadt. And Franz will present us some work he's done around the design of a test setup for experimental investigation of temperature loads on vacuum insulated glazing. Franz, thank you and welcome on stage.
Thank you for the introduction. So I'm happy to be here to present a part of my research today. I will talk about the problems and not the problems, but the challenges to design a test setup and what you have to take care of if you want to test vacuum insulated glazing for a temperature load. So I will present you my test setup today. I will discuss some measurement data with you and show you a comparison with the numerical models and show critical influences on the stress development due to a temperature load on vacuum insulated glazing. So at first, what is vacuum insulated glazing? Most of you know it already. It consists of two glass panes with or without a pump-out tube, depending on the production process. You have one or two low-E coatings to reduce the thermal transmittance due to radiation. You have a edge steel, which is compared to the standard IGU, a rigid edge steel. That means that the two glass panes are actually bonded stiff together, which makes a big difference for the temperature load case on the vacuum insulated glazing. And you have in the vacuum gap, you have a pillar array which is needed to resist the pressure difference between the vacuum gap and the atmospheric pressure. So the VRG actually gives you U values from 0.3 to 0.7 watts per square meter Kelvin, which is quite good. You have a slim and slender construction, and you have a durable construction. The problem is that we have still no harmonized standard for vacuum insulated glass. So that requires that we need to do further testing and development based on that, the development of design and certification standards. So that leads me to my motivation with the basis of comprehensive research of the load cases and the resulting stresses and the resistance of the structure. We can develop these design concepts and from that the standards in the end that will enable the broader application of vacuum insulated glazing and contributes in the end to the energy efficiency of buildings in the future. So what is a thermal load on a VRG actually, and where does it origin? It origins, of course, on the external boundary conditions. So you know an insulating glass unit is always separating two different environments. So we have, of course, the external and the internal temperature, so cold or warm temperature, and the heat transfer coefficients on the internal and external surfaces. That makes the difference or an influence. Also, solar irradiation can have a big influence on the temperature distribution and therefore on the stresses of the VRG. But for today, we won't consider it as we talk about a temperature test setup just due to temperature difference. So the temperature load, which is defined as the average temperature between the two glass panes of the VRG, forms from two different temperature gradients, I would say. The one temperature gradient and deformation is the in-plane gradient. That is comparable, of course, to the thermal bracket scenario of monolithic glass panes. The other thing for the temperature load comes from the temperature distribution of the VRG over the thickness of the VRG. So the temperature difference between the two glass panes of the VRG. And therefore, as the two glass panes have a different temperature, but they are bonded stiff together at the edge, the VRG will bend towards the warm glass pane. And from the deformation, we will receive stresses in the VRG, and for this case, which we will consider today, we will always have the maximum stresses at the edge, right at the edge of the VRG, as you can see from this picture. Of course, from these stresses, fracture can occur in this kind of construction. Therefore, we have to be sure how to calculate them, how to prevent that they get too high, and when does fracture actually happens. So now I come to the test setup. So the test setup is mostly in accordance to the ISO standard, where it is described, but the ISO standard describes a durability test, where the temperature difference of the VRG is not more than or about 40 Kelvin. But with our temperature test standard, we want to investigate the correlation between the air temperatures and the surface temperatures, which is of course connected over the heat transfer coefficient, and in the end on the stress development. Another thing is, of course, that we want to investigate in detail the deformation and the maximum load-bearing capacity of VRGs due to temperature load. After that, we can also investigate the failure criteria. So where does failure occurs? How big is the stress in the end? And that is something which we can, for example, evaluate by the analysis of the fracture mirror. Important, so that's the test setup. So you can choose different test setups, either one chamber or two chamber. We chose that we use a one chamber method. So you have a heating chamber and you have the environment of your room. The test chamber, of course, needs heating coils, a fan, and in the door, the VRG is installed. The installation of the VRG is quite of importance, as you want to, as I said at the beginning, we want to have a free edge condition. That means that the VRG can actually bend freely in plate direction and deform, so there's no constraint at the edge. So that is why we used just two Teflon bearings on the bottom, so that the VRG is only bared vertically. And we applied, we had a few holding blocks, silicon holding blocks on the temperature load side, and we applied some adhesive tape along the edges, so that we can actually have the bearing situation and the VRG can move freely. What we want to measure, of course, is that is the temperature, the deformations or deflections in the VRG, and the stresses in the end. For the temperature measurement, it is really important that you know the temperature gradients that happen in the VRG. You have the temperature gradient in plane, of course. You have the temperature gradients in the pillar regions, for example. In the pillar regions, it's not that a big difference. You have about, or at most, 1 Kelvin temperature difference. But you have to know these temperature distributions in the VRG so that you can apply the sensors at the right point so that you can actually evaluate the measurement correctly in the end. So that's the application of our sensors. We had quite a few temperature sensors on both sides. So on the glass surfaces, which I always noted with a number due to according to the surfaces of the VRG, so 1 to 4, and the air temperatures, which are noted with TI, with I for internal and E for external. And of course, apart from the temperature sensors which we use K-type sensors. We also used to compare the measurement, or to be sure that the measurement is correct, we also used PT100 sensors to compare if the measurement is correct. We also used thermographic cameras and you can see there with an oven temperature of 90 degrees inside, we still have a surface temperature of the VRG on the room side of 20 Kelvin. So that's a temperature step one. So what did we want to do? We always want to apply different load steps. So you can see here the temperature, which increasing over the time for all the sensors. And what you can see that we always apply certain steps. And as the temperature load origins from the deformation and the expansion of the glass surfaces or the glass panes. The criteria for a stable period was the temperature on the surfaces. And from these plateaus, we could always calculate, of course, the mean value to compare later on the measurement with the numerical models. For the start, we had a vertical test setup, as you saw it, and we didn't turn on the fan. And of course, what you can see from here is the temperature stratification. So the temperature in the heating chamber differs quite significantly, as you can see from the graph. For the further slides, we will always discuss only the maximum temperature load which is applied, which is a temperature difference, air temperature difference of 70 degrees Celsius. And you can see here that you have a air temperature difference over the height of more than 30 Kelvin. That makes, of course, the temperature load not homogeneous, and therefore the result has to be interpreted correctly, or we will see later what that means for the stresses. So we had a vertical setup where we had quite a significant difference, or couldn't apply a homogeneous temperature load. So that's why we decided, okay, we need also a horizontal setup. So what does it mean? We just flipped our test setup by 90 degrees and did the measurement again. So with the same sample, and everything was the same. And what we could see from here is that the temperature difference, of course, of the air temperature was more homogeneous. And of course, a more homogeneous air temperature means also a more homogeneous surface temperature, and therefore glass temperature. So it was possible to apply a more homogeneous temperature load, which is really necessary for us, that we can examine later on from the temperature distribution the stresses in the glazing. The third thing was then again a vertical setup, because we have most of the glazing structures in a vertical setup. We used a fan, and the difference by using a fan is that we get way more stable measurement values for the air temperature, of course, and therefore also for the surface temperature. So the top one is the one with the fan, and the bottom without the fan. Yeah, makes sense. If we compare the three test setups, so the horizontal and the vertical without a fan and the vertical with the fan, you can see that the horizontal and without a fan and the vertical with the fan gives more or less the same homogeneous temperature load on the VIG. So yes. And from that, of course, you can see that the surface temperature varies also not that much anymore, so the surface temperature of the glass surface are more homogeneous in the end. Apart from the temperatures, we also measured always the deflection on 2 points, so in the center and in the edge. And you can see that the deflection, they're also coming to a plateau and get stable in these periods, or the period time of holding the temperature load constant was about half an hour or to an hour, and that was enough that we get always a constant period of time of 10 minutes to evaluate them. The comparison with the numerical model, which you can see, is here for the highest load step of 70 Kelvin or 70 degrees Celsius. We have a deviation between our numerical model and our measurement of 200 microns in the end. So it fits quite okay, but okay, we have a maximum deflection of 1.7 millimeters, which is not too much, yeah, but that is okay. So another comparison of the numerical model, or validation of the numerical model, was the comparison with the consisting analytical model in the ISO standard 19916. You can see here from the dark blue dots, that is the numerical solution, so numerical thermal calculation, and the stress calculation was also numerically. The orange dotted line is then used the numerical result from the thermal calculation and use that average temperatures in the analytical solution, which shows quite a good, works quite good together. And the other two lines or dots show what happens if you just use for the measurement data, for example, to use the measured temperature at the center of the VIG and put it and use the analytical model to calculate the stress from that. You will overestimate the stresses which occurred in the VIG. Also, if you use, of course, the air temperature. So in the end, I have two different studies for you. So at first, the temperature gradient, which we had for the first setup. So what happens if you have a temperature stratification in the heating chamber? So we have the same heat transfer coefficients on both sides. We have the room temperature at 20 degrees Celsius. And for the first case, you have a constant temperature, air temperature. In the second case, you have a linear increasing temperature. From that, of course, you have the different temperature distributions, and the different temperature distribution, and we can discuss it later if you want. We get different magnitudes and stresses. Yeah. So what I want to show is with that having the same measurement data from the test setup, it can result in different stresses. So the second numerical study was then by changing the heat transfer coefficient, which is comparable, for example, using a fan or not using a fan. Using a fan is increasing the heat transfer coefficient, so that means that the surface temperature will come closer to the air temperature. In the first case is that we increased the heat transfer coefficient on the heating chamber side, so it's actually comparable to the fan, which leads to, and the second one is what happens if we increase the heat transfer coefficient of the external side. So, for example, the external side of a facade. Of course, we get, again, different temperature distributions here. Don't want to go too much in detail here, but you can see again, we have here for the fan option, I would say, you have 70 megapascal compared to the reference case, it was with 21, so 4 megapascal less. And with the heat transfer coefficient on the external side, we get higher stresses, about 28 megapascal. With that study, I just wanted to show that measuring the temperature in such a temperature test stand only in the center at one point, or maybe also on the surface and on the air in the center region, is not enough to give a reasonable examination of the stresses of the VIG in the end. So we need a more comprehensive knowledge about the temperature load in the VIG to actually evaluate it. So I tried to conclude everything. So we could improve the temperature load, so the homogeneous temperature load, by using a horizontal setup, for example, by using a fan, makes totally sense. And of course, the key influences are the temperature gradient of the load case and also the heat transfer coefficient, so using a fan or not. And of course, you have to be to take care which kind of the temperature measurements you use to calculate later on, or to assume which magnitude of stresses result in the VIG. So the next step is then using the fan and using also deflecting boards, so that we have a really close gap between the deflecting boards, which has a homogeneous temperature already, and bring the temperature even more even on the VIG. After having validated the whole test setup and be able to applying, or to be sure to apply, a homogeneous temperature load on the VIG, we can use it to actually evaluate the maximum temperature load and for the failure criteria of the VIGs due to a temperature load. And of course, from that, we can derive then design concepts later on by having comprehensive test series. Thank you for your attention. I'm happy to answer any questions.
Thank you, Franz. Very interesting experiment.